Hello everyone. In this module we are going to be continuing with our exploration of the idea of pointers, and now what we are going to do is look a little deeper into one specific use case of pointers, which is the implementation of arrays, and along with that we will also look a little bit deeper into the concept of strings. We have informally used strings up to this point when we print things onto the screen and so on. What we are going to be doing at this place is to actually go a bit deeper into that. But first we will start with arrays. So these are more or less the topics that we plan to cover. The first is the concept of an array. What is an array? How do we use it in order to provide structured data storage, and how is this related to the idea of pointers? There is a somewhat tricky part of C related to the idea of pointer arithmetic, where what we do is that we manipulate pointers as though they are just numbers. And in principle, yes, pointers are numbers because after all they are the index of a certain location in memory. But the way that you actually handle these numbers and the kind of operations that you perform upon them, what happens when you add something to a pointer and so on, have very specific meanings in the context of the C programming language. So we will take a further look into that, and then of course we will look a little deeper into the concept of strings. So let us quickly recap where we left off with pointers. What we said was, any time that we declare a variable, let us say int I, what that actually does is that the compiler sees that there is a declaration of a variable I and sets apart a certain location in memory where the value corresponding to I should be stored. The compiler knows that int is supposed to be 32 bits wide. Therefore, it makes sure that 4 bytes of memory are set apart for this particular location. Now, it is important to keep in mind that the compiler does not specify exactly where in the physical memory of the computer that storage is going to happen. And the reason is because I might compile my program on one particular computer and run it somewhere else, and I do not in general know the memory layout of the other computer. I do not know what other programs are running on it, I do not know how much memory it has, and so on. So as a result, what we end up having to do is that we just say, okay, the compiler gives the instruction in the ELF file that is generated saying that a certain amount of memory is required for this variable. Where exactly that memory goes is determined only at runtime when the program actually gets loaded into the memory of the computer. Now, what we saw was, if I have a variable like this declared in this way, int I can use this notation ampersand I, the AND symbol in front of I, in order to get the address of that variable I, and we can then dereference it, meaning that I can take the star of the address and that will give me the data that is actually physically stored at that location. Now, it is important to also remember that this star ampersand I in general is exactly the same as directly accessing I in most cases, right, because after all they are doing exactly the same thing. You have an address, you dereference it. In this case also you have an address and the compiler says to look up the data in that address and get the data out of it. Okay. So both of these instructions out here is pretty much doing exactly the same thing. Now, that is fine when what you want is to declare a single variable. In our case, what very often happens is that we want to deal with lists of data. This is a very common problem that comes up in many different contexts that you can imagine using a computer for, right. And one of the most common sort of sub problems over there would be add a list of numbers. So for example, let us say that you are trying to create a program to just handle the cashier's data entry operations at a market checkout counter, right. You would need to have the ability whereby they can enter a list of prices and there would be something that basically adds up those values and finally prints it out onto a bill, right. Similarly, the marks obtained by a student in order to create their transcript, right, you would need to have some way by which you can create a list of those marks. There are many different contexts which come very naturally in which you would want to use lists of numbers, right. Similarly, I might also have an attendance list corresponding to a class. So, it might be a list of strings, the names and roll numbers of the students who are enrolled, right. So, lists of homogeneous data where essentially all the data points are of the same type more or less, right. Not when I say more or less, the reason is because you might have strings of slightly varying lengths and they would still be considered homogeneous in most cases, right. But in general what we are interested in is we have data of a homogeneous type and we want a list of such data. So, for example, if I have a list of integers, I should be able to create consecutive memory locations ideally for that. An array comes into this context as basically a very convenient shortcut for exactly this, right. In other words, it is entirely possible to have written my program saying that I apple is the number of apples that a person has selected, I orange is the number of oranges that a person has selected, I banana is the number of bananas, and so on. This rapidly goes out of control. Instead, if I just say there is an array I where the first element 0 corresponds to apples, the second element 1 corresponds to oranges, the third element I of 2 corresponds to bananas, and so on, it becomes a lot more compact and in fact easy to even go through such a list and write code corresponding to it, right. I can think in terms of loops and indexes with for loops and so on, rather than trying to type out the individual names of variables separately. So, that is exactly where an array comes in. It is primarily a convenience shortcut, right. You could have achieved the same purpose by directly accessing each of the memory locations. So, what we would like for an array to be useful is that I should be able to specify the starting point of the list, that is where it starts in memory, and probably the number of entries, right. And most importantly, once I have the starting point of a list, I should have some function or some technique or some standard way by which I can reach the next value that is required for this list. Okay. So, those are the primary things that I am concerned with as far as an array is concerned. Pointers help us to achieve that, since after all what a pointer is doing is it's just saying that it is pointing to a location in memory, right. So, if I declare using this syntax int a and use square brackets and say 10 over here, right, what I am effectively doing is I am setting apart memory to store 10 integers, not just one. On top of that, I am also telling the compiler that I want this memory to be a contiguous area of memory, meaning that it is consecutive memory locations, right, where this data gets stored. So, what ends up happening is that one chunk of data, right, a set of locations in memory is set apart for this variable a, right, and how much data does it need to have? I want to store 10 integers, each integer is 4 bytes, that is 32 bits in size. So, the total number of bytes that is present in this block of memory should be 40 bytes, right. And now what I can say is, if I am given the address of any one of those elements, I can compute the addresses of other elements from there, right. And the usual convention is that I am given the address of a of 0, and from there I can go to a of 1 to a of 2 to a of 3 and so on up to a of 9, which is the last element that I have over there. How do I do that? I just say that if a of 0 is at a given address, the next integer can be stored 4 bytes away. So, a of 0, the address, plus 4 bytes will give me the address of a of 1, plus another 4 bytes will give me the address of a of 2 and so on. Okay. So, the important thing of course is that an array has to have consecutive memory locations, right, and this is actually a little important to keep in mind. It is possible that in certain other languages you have the idea of lists or vectors where this is not actually enforced. A list or a vector may have a slightly different memory layout which does not guarantee that memory locations are actually consecutive, right. What it does allow you to do, however, is to traverse the list, to go through the list from one end to the other, right. But in general, being able to access the nth element of a list in constant time by just saying I know where the starting point is and I know where to jump to is something that is guaranteed in C, but may not be guaranteed in the lists or vectors that are used in other programming languages. They have other benefits of their own, of course. So, just to emphasize, these have to be consecutive memory locations when you are building an array, and the second thing is each entry in the array has to have the same size, right. Now, I mentioned a little bit about strings earlier, right, and we will have to get to that a little bit later to study it in more detail. In general, if you have an array of strings, it also needs to enforce that each string is the same maximum size. They may not be individually the same size, but the same maximum size is required, otherwise it actually cannot create an array of strings. Okay. All right. So, a little bit about the syntax that is used in order to declare and work with arrays in the C language. The simplest of course is what we have already seen over here. I can just use the syntax int a of 10, and this will create an array of 10 integers. Okay. I can also use this syntax where I first give const int n is equal to 1000 followed by int b of n, right, and this works because as far as the compiler is concerned, n is declared as a constant, it is not going to change. So, I know that at compile time I can decide that I am asking for a value that is b, an array of size 1000 elements, okay, and this can be decided at compile time itself. Now, this was not there in the original versions of C, but has been there in the compiler for a reasonably long time, so it should work in most compiler versions at this point. Now, you are not restricted only to ints, of course, you could declare a short, right. So, I could declare a short C of 4 where short is a 16-bit data type. And the interesting thing here is, along with declaring it, I am also initializing it. Now, you would have seen that I could in general have something like int a is equal to 5, would have declared an integer variable a and given it the value 5. Here what I am doing is, notice the curly braces, right, the curly brackets that I am using over here. What they are saying is that the actual data that I am initializing out here is an array data type. And what this is saying is actually declare array C as an array of 4 short variables, 4 short values, right, in other words 4 16-bit values, and initialize all of them to the value 0. Actually what it says is initialize the first element to 0, right, and every other value is automatically set to 0 when at least one of the values has been initialized. Okay. Now, why I am saying every other value is automatically set to 0 is, let us look at the next example, which basically declares an array of floating point numbers of size 20 elements. So, the number of bytes over here would be 20 elements times 4 bytes, so 80 bytes totally. I am giving it an initialization vector which basically says 1, 2, and then I use the square bracket notation to say 5 is equal to 3.14, right, and then comma 7 comma 8.2. What happens over here is I take this d of 0 from here, right, the first value which is there in the array, d of 0 is now 1.0, d of 1 is 2.0, but the next thing it says is d of 5 is equal to 3.14. Okay. So, I need to go and make d of 5 as 3.14. What do I do for d of 2, d of 3 and d of 4 instead? They are automatically initialized to 0. Okay. Since d of 5 was given the value 3.14 out here, the next value 7 goes to d of 6, d of 7 gets 8.2, and that is it, I have stopped my initialization. So, the rest of the values basically end up being zeros. Okay. Now, these are some ways by which you can do declaration and initialization at one go, right. Please keep in mind that the notation is not always obvious. So, it is always preferable that you double check and confirm that what you have written is actually going to get interpreted properly by the compiler. In general, C is a language that allows you to make a lot of mistakes without warning you about it, right. So, if you are in doubt, it is always safer to take 2 steps, right, declare an array, initialize it separately using a for loop if necessary, right, or a separate function in order to do the initialization. So, with all of that in mind, now let us look at where in the memory these arrays get defined or declared, right. Now, as we have already seen, if I declare int x, what happens is that the function inside which I declared it has a stack frame, right, a certain area of memory associated with it, and that stack frame is the place where all the local variables of that function go, which means that if I declare int a of 1000 also inside that same function, I will end up creating space for 1000 integers also inside the stack area of that same function, right. And what happens in general is that if we have a view of memory which basically goes from low memory, that is starting at address 0, up to some high memory, which is typically what we think of in terms of the little endian systems, right. What happens when I declare int a of 10 is that a of 0 would typically get a low memory location out here, because I need to have my addresses incrementing. So, a of 1 should have an address that is higher than a of 0, a of 2 should have an address higher than a of 1, and so on, right. And the reason for that is I want to be able to perform pointer arithmetic. I want to be able to work with a pointer that is the address of a of 0 and use it in order to compute the address of a of 1, a of 2, a of 3, and so on. So, in general what you will find is that the layout of memory looks something like this. Let us say that somehow a of 0 got the address 60, it could be anything, right, but let us assume that it is a number 60. What that means is it is byte number 60 in the memory of the system that you are working with. What that means is a of 1 has to be in the next integer location, which is 4 bytes away from 60, which would be at location 64. A of 2 would be at location 68, and so on until a of 9 would be at location 96, that is the location of a of 0 plus 9 into 4 or 36 byte addresses. Address location number 100 is actually just after a of, well, not a of 10, this should actually be a of 9. Right, because what happens is a of 10 is actually outside the memory range of this address, array that I have declared, right. So, what happens is that, remember that arrays, as I have shown over here in C, they always start from the index 0. So, a of 0 is the first element of an array, right. This is potentially a source of confusion for people who are new to programming. The reason is because human beings do not think 0 indexed, right. We do not start with the 0th element, we start with the first element of a list, right. But in terms of convenience, in the C programming languages and in several other languages including Python, right, what ends up happening is that we use 0 as the starting index just because of convenience, because of the way that we actually compute addresses in memory, right. Because if I can do that 0th indexing, I can say that the address of a of 0 is the actual location at which this array starts, right, and all that I need to do corresponding to a is to keep track of that address, right, which means that if I have 10 elements, I go 0, 1, 2, 3 up to 9, not up to a of 10. So, a of 10 is technically outside the array that I have declared. So, again keep in mind that this particular diagram that I am showing over here, where a of 0 is at the lowest address and a of 9 is at the highest address out here, corresponds primarily to little endian systems which are going from low memory to high memory, right, whereas big endian systems, which you can think of as having a left to right view of the memory layout, would probably have it the other way around, right, because I still need to have the condition that the address of a of 1 is 4 locations higher than the address of a of 0. That is my constraint which is set by how pointer arithmetic works.